Welcome to Tripoli 301 Digital Electronics Register and Counter Part 2. Okay, so we'll discuss about the ring counter. Ring counter is a typical application of shift register. The only change is the output of the last flip-flop is connected to the input of the first flip-flop. So if you look at here, the output of last flip-flop is connected to input of first flip-flop. The output of first flip-flop is connected to the input of second. Output of second is connected to input of third. Output of third is connected to input of fourth. Okay, so here the clock is same actually. If you look at here the clock, so first clock, this is the same clock, this is the same clock, this is the same clock. Previously the output of first flip-flop was working as a clock for second, and output of second was working as a clock for third, like that. So it's kind of different in terms of construction with the previous flip-flop. Okay, one more thing is it has override. ORI means override, which means if override will be activated when you see, so when override activated, it will activate the preset and clear, PR and clear. So preset is this is bubble, so preset is low, clear is low. So that means if override activated, then preset low, clear low. So preset low means is setting the flip flop to 1, and clear low means it's setting the flip flop to 0, clear 0, set 1, clear 0, right? So it will be only activated when your override is activated, right? Reset and clock clear will be activated with when override is activated. Okay, and one more thing is previously the number of state was uh, not equal to number of flip flop, right? So number of state was 2 to the power p. P was number of flip flop, but right here you have 4 flip flop, so you have 4 state as well. It's not 2 to the power p, right? And it will count the same 2 to the power p minus 1. That means 2 to the power p means 16, 16 minus 1, so 0 to 15 it will count, right? Okay, so we already discussed about this, but I want to emphasize on this truth table. Okay, say like your override is low, so low means override is activated, right? So if override is activated, so this is taking the charge, so it doesn't matter what the clock is, right? It is getting the priority because this is asynchronous action. So if it is getting the priority, then what will happen? Just consider all of the flip-flop initial value was 0 0 0 0, right? So if your override is low, that means this got low, so your preset got activated. So preset will set the values here to 1, so your q naught will be 1, so your q naught will be 1, and previously here your value was 0, so q 1 will be 0, q2 0, q3 0, so 0 0 0. So all are shown as a green color, so 1 0 0 0, the output of the fourth flip-flop. Okay, in the next cycle your override gets high. So override high means then it got deactivated. That means all the register will now act as a synchronous counter, you can say, or it will be activated through clock. So as it is says it's falling edges clock, so it will activate it falling edge clock. So the initially, so here the green color, so this 0 will be coming here, so its input will be 0, right? And as it is a D flip flop, so if input 0, output 0, so output will be this color, kind of a bluish color, violet color, so this will be 0. Then this 0 will be here for the second clock, so first and second. For the second clock, this is your output, and your initial value was 1 here, so it's getting here 1. So if D1 1, Q1 will be 1. So Q1 for the second one, Q1 will be 1. So this is second clock, Q1 will be 1. So here the output was 0. So 0 will be going here. If input 0, output will be 0. So it will be 0. So it will be 0. So if you keep going for the third one, so like here, so here your input is 1, right? So the output will be 1. So output will be 1 and other will be 0. Same way this one will be 1. And if you keep going, here you'll be get again 1. Okay. So if you look at here, so this one is for preset, right? And later on, when your override is low due to the clock, this would go transfer to other flip-flop. So it's kind of shifting the one into different flip-flop. That's why it's typical application of register, shift register, you can say. Okay, so it produces a ring kind of cycle if you look at here, right? Also, if you look at the output, so this is our clock, and override initially it was 0, later on it was high. So 0 means override is getting the priority. So in this region, that's why your key unit is 1. But whenever override is high means your clock got activated, so it will work at clock edge. So if you look at here, so in clock edge, so it will be changing the state. So it becomes 0 to 1. Next clock edge, 1 to 0. Next clock edge, so your input is 0, output will be 0, right? Here 0, because this is a D flip-flop. So if you keep going, so it will be 0 for the other clock edge. And for Q2, this is same. So initially it was 0, so it will be 0. So this is your clock edge. So this clock edge it will change to 0 to 1, right? And again this clock edge it becomes 1 to 0, right? Because the output, say output of Q naught will be input for Q1, output of Q1 will be input for Q2, output of Q2 will be input for Q3, right? Okay, so here it becomes 1 again. So this is 0, the output will be 0. This is 0, output will be 0. So for this one again here, so it will be changing state as the clock edge here. So 0 becomes 1. And next clock edge it will change its state, and for input 0, output will be 0. Okay. So if you look at here, so 1 1 1 1 1. So it's creating a clock. So that's why this is clock ring counter is forming a ring kind of structure. So number of state will be 8, and we'll see how it's counting the values. So initially clear is 0, so your Q naught is 0, and when your clear is high, then it's looking for the clock. So clock is here, it's changing its state 1. But if you look at the other counters, it's supposed to change its state this clock edge, or change its state this clock edge, right? But it's not doing it because of this one, this feedback, the negative feedback. It's always taking 4. We have 4 clock, sorry, 4 flip-flop, 1 2 3 4. So it's keeping the values 1 1 1 for 4 clock edge, then it's changing state. The second one same, taking the values for 4 clock edge, then changing state. Same one, 4 clock edge, changing state, 4 clock edge, changing state. Also if you look at here, so just for 1 clock edge it is 0, then 4 1, then 2 clock is 0 4 1, 3 clock is 0 4 1, 4 clock is 0 4 1, something like that. Now actually, how actually you are getting these values? Okay, just look at here. So all the flip-flop has the 0 0 0 0 0. Okay, so what will happen, when we are at this situation, like clock is clear is 1 and clock is activated, falling edge, right? Just here. So these values becomes 1, it's coming here, right? So this is 1, and previously here the input was 0, so it's going here. So these zeros goes here, and again these zeros goes here, these zeros goes here, these zeros goes here. Look at the color change, okay? And for this one, so this one output becomes 1, right? And this one goes here, and for this one the output will be 1. This is this one, and this one goes here as the input, and this one output becomes here 1, and again this one goes here, so 1 will be here, and this one will be going there. So if you keep doing this, so you'll see, so it becomes, initially it was 0, so initially it was 0, and for other forces it will be 1 1 1 1, something like that. So 4 1, one more state is not showing here. So you can show it here if you like, or you can just draw the timing diagram directly. Again here 0 0, then 1 1 1 1. For the output here will be 0 0 0, then 1 1 1 1. Here will be 4 0 4 1. So that's what is happening here, right? So this is the Johnson counter. So this is the truth table here. So initially it was the first clock, right? First clock was 0 0 0 0, then 0 0 0 1. So 0 0 0 1. The third one will be 0 0 1 1. Fourth one will be 0 1 0 1 1 1. 0 1 1 1, and the fifth one will be 1 1 1 1. So 1 1 1. Next one will be 1 1 1 0. So 1 1 1 0. Next one will be 1 1 0 0. So 1 1 0 0. And next one will be 0 0 0 1. Last one will be 0 0 0 0. So that's all. So just look at here, 4 flip flop, we have 4 into 2, so 8 state, right? And this is not like it's not counting 0 to 15 or something like that, so it has kind of special kind of numbering, right? It's not following the sequence. So just if you look at here, 4 0, then 3 0 2 0 1 0, then all 1, again 1 0 2 0 3 0 4 0. Uh, it's following a pattern actually, right? Okay. So this is a special kind of counter. This is called Johnson counter. So now we'll discuss about modulus of counter and counting after particular value. So say like mod number equals to the power n. What is mod number? What is n? N is number of bit. So 2 bit means n equals 2. So 2 to the power 2 is 4. So 2 bit triple counter is also called mod 4 counter. 2 to the power 2 is 4, right? So mod 4 or modulus 4 counter. 3 bit triple counter is 2 to the power 3 8. So mod 8 counter. Okay. So the counter can be um, defined as 2 bit, or it could be mod 4. It could be up and down both, right? So 2 bit up down or mod 4 counter, 3 bit up down or mod 8 counter, 4 bit up down or mod 16 counter. So this is the concept. So instead of say like 2 bit or 3 bit counter, so in the exam you may be asked like mod 4, mod 8 or mod 16 counter as well. Okay, so there will be some question in the next slide, couple of slide. So you need to find the answer for this mod counter. Okay, this is pretty important concept. Anyway, so discuss about the register in the next section. Thank you.